When we left off, I had gotten the score digits and the lights on the back box and lights on the playfield working. The next step was to get all of the switches working. So the contact switches for the pop bumpers and the stand-ups and the slings, and also the optical switches for the scoop and the shooter lane and the trough, and the push button for the start button. I wanted to get all those switches working. You know, it's been a little while since I had worked on this project. I had kind of set it aside to do some maintenance on my full-size pinball machines. So I'd kind of forgotten where I was. I'd already done a lot of circuit analysis on both the playfield and the back box. Traced out all of the switches and optos and lights. So, just to reverse engineer the micro connections, I had to do some basic circuit analysis on all the components. But to get them working individually, and especially to get the switches working, I needed to go kind of back to basics on it and look at each individual circuit discretely. So the stand-up switches, how does each one of those work on the playfield? Trace it out, kind of draw the circuit diagram just to isolate that one circuit so I can figure out how it works. And I wanted to do that for each of the major components in the machine to just kind of refresh myself with how the machine works and make sure I really understand how each of the circuits work before I apply power to them and try to drive them with a micro. So let's take a look at each of the individual circuits for the lights and the switches on this machine. So when I went to take a little more in-depth look at each of the circuits for the lights and switches, I started with the lights because I already had them working, and I had done a good amount of circuit analysis already on the LEDs in the back box, how those are wired, and also the LEDs on the playfield. I'd already traced all of those out, but when I was tracing them out, I was really only looking for how they connected to the microcontroller, because I wanted to draw this diagram here of what each of the pins on the micro did. So I wasn't really looking too in depth at the components that were in line on these traces. Like you can see a resistor here and a transistor there. I was just looking at how they connected to the microcontroller. So I took a more in-depth look at each of the circuits for each of the LEDs, and I came up with 3 different types of LEDs. Here at the top left are the LEDs that you can see marked in red on the playfield that are controlled directly by the microcontroller. So it's a pretty simple circuit where the power runs through a resistor and through the LED to a pin on the microcontroller. Next, the LEDs in purple. You can see they're on, there's some on the playfield and there's some on the back box. Those are much the same, where you've got power coming in through a resistor through the LED to a pin on the micro. But in this case, it's the slave microcontroller, and the state of that pin is controlled with the SPI bus from the main microcontroller. So these two up top are pretty much the same. It just depends on which micro is actually syncing the current for the LED. The one that's different is the bottom left here, with the inline transistor. So this is only used for 2 different LEDs, and they use the same pin on the microcontroller. So really this transistor is here to allow 2 LEDs to be controlled by the same pin. So it's used for the two top pop bumper lights, F and H here. The micro is still either syncing or sourcing current, but in this case, both of those LEDs turn on or off based on the state of the pin of the micro. So all of the LEDs, I don't know how many are here, there's a lot, you can see on the playfield and backbox. They're all connected via one of these three different types of circuits, either directly controlled by the microcontroller, or directly controlled by the slave, or controlled by the microcontroller through a transistor. So let's take a look at each one of these in more detail and see how we can program the Teensy microcontroller to control each one of these three different types of circuits. Let's start with the most simple LED circuit, where the LED is directly controlled by the microcontroller on the playfield. Now, my goal with drawing these simple circuits was to isolate the circuitry for the LED and make sure I knew how each of the different types of LEDs worked. Similarly, with the Arduino code, my goal was to isolate just the minimum amount of code I needed to control each of these three different types of circuits. Now, I've been working on this project for several months, and during the course of reverse engineering how the machine worked, I wrote a lot of code. So I've got a large amount of code that I've developed so far, and I've kind of got an architecture in works, but when I stepped away from this project for a few months, I forgot how a lot of it worked. So I wanted to go back to basics, write the minimum amount of code that I could to get the LEDs working, and kind of relearn how each of these different types of circuits works. So in the case of the LEDs that are directly controlled by the micro, this is a pretty simple implementation of what it takes to control one of those LEDs. So just like in the circuit, we've got one pin on the micro that is configured as an output pin. So it's either sourcing current or it's sinking current. When it's high, it's sourcing current, and when it's low, it's sinking current. So in the case of this circuit, we've got power coming in from the playfield. That LED is going to have a path to ground when the pin is configured low. So we configure the pin for output. We turn the LED off. We wait a bit. Turn the LED on, and then wait a bit. Now, in this case, the pin that we're controlling is the top bonus light right here. But this same program could control any of these pins here that you see. The pops, or the left stand-up, or the middle bonus light, or the right post. Because all of those different LEDs use this same circuit. But for now, the way this program is written now, it's controlling the top bonus LED. So let's load this onto the Teensy and see it in action. I'm going to disconnect the power supply coming from the Teensy, going to this rail here, which is powering the playfield circuitry. I'm going to disconnect that so that I've only got power going to the Teensy before I connect it to USB. Otherwise, it would try to power the entire playfield off this USB connection. and I don't think the regulator in the Teensy is strong enough to do that. So let's compile this small program and upload it to the Teensy. We'll disconnect USB power, reconnect, power to the playfield, and hook up the battery box to my bench supply, which is currently outputting 4.5 volts, just like the batteries would be. And you can see the top bonus light blinking, just like we have it programmed to do here. So it turns on, and it waits 500 milliseconds, and then it turns off, and then it loops over and over and over again. So it's pretty much the most simple program you can write on the Arduino that will control any of the LED circuits that are connected the way it is here. Next, let's take a look at LEDs that are controlled by the slave microcontroller in the backbox. So that's any of the LEDs that are marked here in purple. Now that works pretty much the same as where it was directly controlled by the main microcontroller, except now it's being controlled by the slave. So the slave still has an output pin that's either high or low, and the light is turned on when the pin is low. But in this case, the Arduino code isn't controlling this output pin. The Arduino code in this case is communicating information via the SPI bus to the slave microcontroller and telling the slave microcontroller to turn off or on that LED, or to set that output pin is high or low. So let's take a look at the code that it takes to do that. Now there's a bit more code here now because we have to implement that SPI protocol, and there's a fair amount of data that we have to push across to the slave microcontroller to make it work. So just like before, we've got a setup function and a loop function. Let's take a look at the setup function. In the setup function, we are configuring each of the 3 pins that it takes to implement the SPI protocol: the chip select bit, the master out slave in bit, and the clock bit, or pin rather. So we configure each of those pins as an output, initialize all of them, wait about a millisecond to make sure that takes effect, and then we send some data. So we've got this loop here that communicates a number of bytes. And for each of the iteration of the loop, we're sending 2 bytes from this startup message structure. So let's take a look at that structure. It's an array of bytes. And to be quite honest, I don't know what this stuff means. But as we saw in a previous video, when I used a bus analyzer, this is the data that I saw the microcontroller output to the slave. when you first turn the machine on. So it's initializing the slave with something, and it's contained in these bytes. So I'm just mimicking what I saw the master microcontroller do using the bus, what I saw it do using the bus monitor. So we start out by sending this structure of bytes across to the slave 2 bytes at a time using the send word function. So let's take a look at that send word function. That's right here. It takes as an argument 2 bytes, the first byte that we send and then the second byte that we send. In a previous video I showed how SPI works. You might want to review that if you haven't seen it or forgotten. But the first thing we do is set the chip select bit low. That tells the slave that this information that's coming across the bus is intended for you, so pay attention to it. So we set that bit low. We delay a few microseconds to make sure the slave has seen the transition. And then we use Arduino's shift out function to push some data across on the MOSI pin. And the data that we're pushing is the first byte. So we send all of the data, most significant bit first, from the first byte, and then we do the same for the second byte. Then we set the chip select bit high to tell the slave that we're done, and we wait a few microseconds to make sure it sees that transition. So in that way, during setup, we're sending this initialization message 2 bytes at a time to the slave. After we finish that, we wait about a millisecond, and then we move on to the loop function. So just like before, this function runs over and over again for as long as the micro is powered on. In this function, we're using an array of bytes called state message. This is the information that we're going to send across to the slave. So the first thing we do is we initialize that array of bytes to a default. Let's take a look at that default. So here's the default of the state message. It is 8 bytes long. And I don't know what all of these bits do. But it's just through experimentation and manipulation of the structure, I figured out what some of them do, and I've got them labeled here. So these first 3 bytes, I have no idea what they do. I really haven't played around to see if they have any effect. My guess is if I manipulated some of these bytes, it wouldn't. The slave micro wouldn't even take this information. It might just ignore it. But I really haven't tried. So I've only messed around with the bits that are noted here. So in the 4th byte, these bits control the 7-segment display on the score display. This last bit controls the arrow or dot under or after each of the digits. So in general, this byte controls what is displayed in the score display. Then the 1, 2, 3, 4, 5, 6th byte controls LEDs in the backbox. So this bit is the bottom 2 lights in the backbox, here, Y and Z. And this next bit is the top light in the backbox next to the score display, light X. And then the next bits control which digit in the score display that this byte is controlling. So depending on how you set this, you might be controlling, the first digit in the score display and its arrow, or the second digit in the score display and its arrow, and on down the line. The 8th byte has the rest of the LEDs. So these bits here control LEDs K, G, S, Q, R, and P on the playfield. So all of the LEDs in the playfield that are marked in purple. So every iteration of the loop function, we're sending this structure of bytes to the slave and manipulating the bits inside of it to have some effect. So we start in the loop function by copying that default state. So in this case, all of the bits are set to most of the bits are, for the LEDs at least, are set to high by default, so they're all off by default. So we initialize all the LEDs to off by copying those default values into the array. And then, just like in the previous code that we looked at, we're switching a bit between off and on and off and on. So the first thing we do here is clear the bit, set it to low, which is turning the light on. The bit that we're changing is the 0th bit, and the byte that the bit is in is the 7th indexed from 0. So let's take a look at which bit that is. This would be the 0th byte, and then the 1st and 2nd and 3rd and 4th and 5th and 6th and 7th. So we're controlling the last byte, and we're controlling the 0th bit in that byte. So the least significant bit, which is LED P, the bottom bonus LED, this one here. So the first thing we do in the loop is clear it, which would have the effect of turning the LED on if we were to send that buffer across the SPI bus. But we aren't sending it yet. All we're doing is modifying the data in this array. In this array here. So we set the bit to 0, and then every half second, so this is a counter of the amount of milliseconds that has the duration that the microcontroller has been running. If we mod that by 1,000, we're left with a number between 0 and 999. If it's greater than 500, then we're going to set the bit. So we'll, in that last byte, 0th bit, we'll turn the bit on, which would have the effect of turning the light off if it's greater than 500. So half the time, we're going to turn the set the bit to 0. Half the time, we're going to set the bit to 1. That would have the effect when we send the data of turn the light on or turn the light off, and toggling it every half second. So after we've manipulated the bit in this array of bytes, we need to send that array of bytes to the slave microcontroller, and that's what we do in this last bit of code down here at the bottom. So we're going to loop for the length of the array, which is 8 bytes long. Every iteration of the loop, we're going to send 2 bytes, the first and the second. So this has the effect of sending this byte, and then this byte, and then this byte, and then this byte, and so on until we get through with the array. And just like the initialization code at the top, we're using the sendWord function that we saw up here. So sending 2 bytes at a time using this function. So recap, we're initializing the 3 SPI pins that we need to implement the SPI protocol. We're sending a binary blob of initialization code from the master to the slave. I don't know what it does, but it gets that slave working. Then we are changing 1 bit at a time in this message. In this case, we're changing the very last bit, which controls LED P. We're toggling that bit between 1 and 0. When it's 0, the light's on. When it's 1, the light's off. Toggling it every half second. And then we're sending, every time we toggle it, or every iteration of the loop, we send that entire message to the slave. So let's build this and load it on the micro and see what it does. Disconnect the Teensy from the playfield power. Got the Teensy, got the playfield removed from power. We'll compile this code. And push it to the Teensy. And let's see what it does. Pick the playfield up to 4.5 volts. And there we go. So you can see every half second, LED P, the bottom bonus light, toggles on and off. That's because we're setting that bit in the SPI data either to 1 or to 0. And the LED is on when the bit is 0. So this same code would work for any of the LEDs that are controlled in this byte array. So Y and Z are controlled by this bit, X by the next bit, and then K, G, S, Q, R, and P by these bits. So this code can control any of those LEDs. Now for the third type, where the LEDs are controlled by the transistor, the circuit is different than what you see up here in the directly controlled circuit diagram. But the code is actually the same. From the microcontroller perspective, the micro is doing the same thing when it's controlling these 2 LEDs as it did when it was controlling just a single LED. So we still have an output pin in the micro that's either sourcing current, where the LEDs will be off, or sinking current, where the LEDs will be on. So this This type of circuit is only used for one set of LEDs, F and H. That's the two top pop bumper lights. So let's modify this code that we looked at before when we looked at this circuitry. Let's modify the code to control the pop bumpers. It was controlling the top bonus light, so we'll change it to control these up here. And just prove from the Teensy's perspective that it's the same code. So previously this pin was set to the top bonus LED. Let's change it to the pin that controls the top pop bumpers. Pops top, which I've got as pin 18 on the micro. We'll leave the rest of the code the same because the micro does the same thing to control these two LEDs as it did for the other LEDs. We'll disconnect the Teensy from playfield power. Got disconnected from the power supply. And let's upload this code. We'll recompile it with the new pin and push it to the Teensy. So now that the Teensy is controlling pin 18 that I've got connected to those two pops, we should see those flash the same way that the bonus light flashed before. And there we go. So now when we're toggling the pin in the Teensy, it's actually controlling a transistor, which is sourcing current for the two LEDs simultaneously. So one pin, two lights. But it's the same code as if the micro were controlling just a single LED. So that takes care of all of the lights on the playfield and the backbox, except for the lights that make up the 7-digit displays here. So let's take a look at the code that it takes to control those. It's not like the code that controls the LEDs that are used for the playfield or the backbox, though it does use the SPI connection between the microcontroller and the slave. So if we take a look at the code, it's more like the slave-controlled SPI LEDs that we took a look at earlier. We've got the same state message here that we send to the slave microcontroller, except now instead of changing the LED bits here or here, we're now changing the individual bits for each of the 7 segments, 8 segments if you count the dot or the arrow at the bottom. But we'll just stick with these bits that control each of the 7 segments. So top left, bottom, bottom right, middle, top right, and top. So there are 8 bits in that byte represented here. The most significant bit controls the middle segment, so the middle line that bisects the digit. The next bit controls the top left segment. Next bit controls the bottom left segment, and so on. So if we want to set, let's say we want to set the middle segment in a digit, we would set, in this byte, we would set the first bit, so this one. And that tells the slave microcontroller to turn on the LED for that middle segment. If we wanted to set more segments in that digit, we would set more bits. So there could be any number of bits in this byte turned on, and it would turn on the individual segment in the digit. Now there are 1, 2, 3, 4, 5, 6 digits in the display, so we also have to tell the slave microcontroller which digit we're talking about. And we do that by setting one of the lower bits in this byte. So the first 2 high bits control the LEDs in the back box, this LED and these 2 down here. The remaining lower bits in this byte tell the slave microcontroller which digit we're referring to. So if we want to set the leftmost digit, this one here, we would set the least significant bit and turn that on. If we want to manipulate the next digit, the second digit, we would set the next bit higher, and so on and so on. So, and that way we can control each of the 6 digits, and we do it one at a time. So every digit we want to manipulate, we send a new state message. And each state message, we can manipulate any of the segments in that digit. So multiple segments per message, but only one digit per message. So you can see that we would, to control, if we wanted to manipulate each of the digits, each of the 6 digits, we would need to send this message 6 times. So let's take a look at the code that does that. We're still using the same send word function, still sending the same state message, sending it 2 bytes at a time. Still using the same SPI pins, still sending the same initialization message that we did before. But you can see the loop is different. So we're still sending the same state message. We still initialize it the same. But now we're manipulating up to 6 digits. What I'm doing in this code is displaying the hello message that I displayed in an earlier video when I first figured out how the digits work. So in the first digit, we'll want to display an H, and then an E, and then an L, and an L, and an O, and then this last digit is blank. Now this is kind of interesting because the game from the American Girl factory, with the software that it comes with, only displays numerals, so just a score digit. But because you can individually control each of the 7 segments in each of the digits, you can actually display some rudimentary alphanumeric characters, letters, and maybe even some graphics. Since you can control each of the segments, you could make patterns using the individual control of the segments. So it's something that was built into the software that, or built into the hardware that the software didn't take advantage of. But we can take advantage of it here. So we'll display characters, alphabet characters, instead of numbers. You can see this conditional here is addressing each of the first 5 digits. I've got a counter up here that starts at 1, and every time we go through this loop, we will increment that counter by 1. So we'll do the first digit the first time, and then the second digit the next time, and the third, and the fourth, and the fifth, and the sixth. Once we get above 6, then we'll reset it back to 1. So every time we go through the loop, we control one of the digits. And the next time we go through the loop, we control the next digit. So the first time through the loop, when we're controlling the first digit, we need to set the segments in that digit to make an H. So we're going to set the top left segment up here, then the top right segment over there, then the middle segment, then the bottom left segment, then the bottom right segment. So in that way, we'll form an H. So in this 1 byte, we're enabling multiple bits. And then we tell the slave that the digit that we're trying to control is the first digit. So we're going to set this bit in this byte here. So there'll be multiple bits set here, and only one bit set amongst these bits. The bit that is set tells the microcontroller which digit we're referring to, and the bits here tell the microcontroller which segments of that digit we want to enable. So we'll set the segments here, tell it we're trying to control the first digit, and then we fall down to the same code that we had before, where we send that state message to the slave microcontroller. So the first time through this loop, we'll control the first digit and we'll make an H. The second time through the loop, we want to make an E in the second digit, and we do that by enabling some different segments and then telling the microcontroller that we want to refer to the second digit. Third time through, we'll make an L in the third digit. Fourth time through, we'll make another L in the fourth digit. Fifth time through, we'll make an O in the fifth digit. The sixth time through, we do nothing, right? Because this digit is blank, because all we're saying is HELLO, and then we're doing nothing here. So the sixth time through, we don't set anything here, because we're telling the micro we're not even trying to make any changes to the digits that are being shown, and we don't set anything here because we have no segments to turn on. So this is kind of a no-op case, but we still send the state message. Because when the pinball machine is actually running, maybe your score is only 100, right? So you're only filling in these digits, you're not doing anything with these digits, but you still want to control the lights that are on the playfield. So you still need to send another state message to the slave microcontroller, even if you're not changing any bits in some of the segments. So anyway, each iteration through the loop, we're going to control a new digit, and we'll set the segments depending on which characters we want to show. So let's compile this and upload it to the micro and see what happens. And there we go. So if you put all of these different types of lights together, you can actually get a pretty decent light show going. Check this out. Next, let's take a look at the switches. There are three different types of switches on the playfield. There's the push button for the start button on the front of the machine. There are some exposed contacts that are used for the slings and the posts and the pop bumpers, where the ball makes electrical contact between the two contacts. And there are optical switches that are used for the trough and the shooter lane and the scoop, where the ball breaks an infrared beam that goes between an emitter and a receptor. Each of those three different types of switches corresponds to a different type of circuit. So there are three different types of electrical circuits in use here. There's the push button for the start button, the direct contact where the ball makes electrical contact across the switch, and there's the optical switches. Let's take a look at all three of those. First, let's look at the push button used for the start button on the front of the machine. So if we take a look at the circuitry on the playfield here, the traces are long, but the circuit itself is pretty simple. You've got power going through a resistor, and then going through the contacts on the push button between power and ground. So kind of isolating that circuitry and taking a look at it more closely, we've got power coming in from the playfield here, going through a pull-up resistor, and at that point, if the switch is closed, it has a path to ground. If the switch isn't closed, then it doesn't. And the microcontroller is looking right at that point before the switch. So if the switch is open, like it's shown here, there's no path to ground, and the microcontroller will see high. It'll see voltage here, positive voltage here. If the switch is closed, then all of that power is going to go straight to ground, and the microcontroller is going to see very low voltage, if any at all. So it's going to show low at that point. So in code, we've got an input pin that normally registers high, but when the switch is closed, it registers low. So when we push the start button, we'll see low. So let's take a look at the code for that. So the code's pretty simple. I've got the start button pin, this input pin here, connected to pin 19 on the micro. I'm indicating closure of that switch using the top bonus LED. We configure the pin, the start button pin, is input, and like the other code, we'll configure the light as an output pin. And then all we do is read that input pin. If it's low, if there's not much voltage sensed because it's all going to ground, that means the push button has been closed, the switch is closed. So the button is being held down. So when that happens, I'll turn the light off. If the switch is open, like it is right now, then I'll turn the light on. So let's load this code up. Alright, so we've got the bonus LED on, and if I push the start button, it turns off. So that's all the code it takes to make the push button work that's used for the start button. Next, let's take a look at the type of switches where the ball makes direct electrical contact. So you can see on the playfield we've got, on the pops for instance, an electrical conductor on the playfield surface, and then another conductor that's sticking straight out of the playfield. These aren't connected together until the ball makes contact between them and closes the circuit. If you look at the circuit diagram here, you'll see some similarities where there's an input pin on the microcontroller and a path to ground that gets closed when the switch is closed, when the ball is making contact between these two conductors. But there's a difference here in that the power doesn't come from the playfield, it comes from the microcontroller. So if you take a look at the circuit here, this is the connector that goes to the playfield. So past this point on the playfield, all we have is electrical conductors. There's no other components. So what we have is a direct connection from the microcontroller through a resistor to the playfield and then back to ground. So there's no source of power in this circuit here. Now this is a capacitor that goes across the switch contact, and there's a voltage suppressor that goes along with that. But there's no connection to VCC that we see anywhere, which was interesting to me, and it took me a minute to figure out what's going on here, and that in this case the microcontroller is providing power. And it does that using an internal pull-up. So let's take a look at the code. This is the code for the push-button switch. The code for the exposed electrical contacts is very similar, with one important exception, and that's this. So previously, the pin was configured for input, but in this new circuit, it's configured for input pull-up. So that one change tells the microcontroller to not only sense whether voltage is high or low in the circuit, but also provide a source for that high voltage. So the microcontroller provides the 3.5 volts that would have been provided by the playfield in the previous circuit. Provides 3.5 volts, sends it through a pull-up resistor, and this is all internal in the microcontroller. And then the point of sensing the voltage is right there after the pull-up resistor. Now outside of the microcontroller, all we see is a connection through a resistor, through a switch, to ground. So when this switch is open, as is shown here, and there's no electrical contact being made by the ball, then the input pin shows up as high because it's sensing this internal voltage source. When the switch is closed, when the ball is making contact between the two conductors, then there is a path to ground, and the pin shows up as low because all of that voltage is being sent to ground. So it makes the circuit on the outside of the microcontroller pretty simple. All we've got is a one pin with a path to ground. And it's because that voltage source is coming from the microcontroller itself through an internal pull-up. So the code is pretty much the same as it was in the previous circuit. There are a couple exceptions. This type of code could be used for the pops or the stand-ups or the slings. So I've got 3 different potential pins I can use here. Still using the top bonus light to indicate whether the switch is open or closed. In this case, the code is looking at the sling switches, so these two. By the way, these are both electrically identical, so the code can't tell the difference between a left sling hit or a right sling hit because they're the same switch. You can see in the circuitry here that we've only got three different lines here. The slings are a single pin. Both of the slings share a single pin. Both of the stand-ups share a single pin, and all three of the pops share a single pin. So we can't tell which pop was hit. We can only tell that one of them was hit. Same with the slings, and same with the stand-ups. In this case, the code is looking at the sling switches. The other difference here is that we're configuring the pin, the sensing pin, as an input with a internal pull-up. So that enables this circuitry here. Still using the top bonus light to indicate closure. And then reading the switch is the same as it was before. So if we see the pin is low, then that means there is electrical contact between these two. The ball has made contact with the conductors. So in that case, we'll turn the light off. If the pin is reading high, then there is no electrical contact between them, so we'll leave the light on. So let's load that up and take a look at how that works. So the bonus light's on, meaning that the switch is open, there's no electrical contact, and I'll just make electrical contact between the two slings here. So the switch is closed, open, and they both work the same. Let's just try that with a ball, because that letter opener makes pretty solid contact. The ball, on the other hand, not such great contact, and you can see the light gets a little flickery. It's not until I really push the ball against those two contacts that it's solidly off. Otherwise, lots of flickering going on. So I'll have to remember when implementing the game code for the machine to do some debouncing here. Maybe the very first instant that I see a switch get hit, I'll register that as the switch being hit, and then maybe I'll ignore the next a few milliseconds, so that I don't, if I get 10 points for every sling hit, it doesn't go 10, 20, 30, 40, 50 as the light blinks. I'll only get awarded the first 10 points and then ignore the next few hits for a few milliseconds. And that kind of flickering it's not, I'm looking at the slings now, but it's the same on all of these different exposed contacts. So we'll have to do some debouncing in the code once I get to the code for the rules. Last are the optical switches used in the trough and the shooter lane and the scoop. These were the ones I was most interested in taking a look at, because there's a lot more circuitry in play here. Now granted, the circuitry that I'm showing here are for all three of the switches. So individually there's not as much. If we take a look at the scoop, for instance, there's two pins used on the micro, and they go through two resistors and the emitter and receptor of the optos, and they get power from this trace here. So there's not too much going on, but I wasn't that familiar with optical switches that are wired like this. So I went and take a look. I was anxious to see how these work. You can see from the circuit isolation here that we've got power coming from the playfield. That's going to a infrared emitting diode, and then a photodiode that acts as the receptor. So the power goes through the emitter, through a resistor, and that current is synced in the microcontroller. Similarly, power goes from the playfield through the receptor. That receptor will conduct as long as that infrared is hitting it. When infrared stops hitting it, it's going to conduct less, or not at all. So assuming the infrared is hitting it, the power goes through that receptor, through a resistor, and to ground in the micro. Then you've got the microcontroller with an input pin that is sensing the voltage past the photoreceptor. So if this receptor is conducting, in other words, if IR is hitting it, if the beam is not broken by the ball, then we're going to see high here. This input pin is going to see high. Once that beam is broken, then the receptor conducts less or not at all, and we'll see low because there won't be voltage present here because it will have been stopped by the receptor. So we'll basically see the ground side here. Now, what's interesting is they could have gotten away with just using one pin, just the input pin, but they chose to ground both the emitter and receptor inside the micro using an output pin. And I'm guessing the reason for that is so that they can kind of turn off this whole circuit. Normally we'd have the output pin set to low, which would provide a path to ground for both of these diodes. But they have the option of setting it to high, which doesn't provide a path to ground. Or maybe some kind of floating tri-state, where these LEDs, the LED and the photodiode, don't have a path to ground at all. So maybe if the machine goes into power save, they can configure this pin somehow so that it's not we're not blasting IR all over the place in a power save mode. Maybe we can lower the toll on the battery. But it's interesting that they've got 3 optos in play here, and they chose to use 3 pins, 3 additional pins, when they could have just grounded this straight to ground, straight to battery ground. So anyway, 2 pins in use here. One output pin that I'm calling the enable pin that enables the circuitry when I set it low, and then the input pin that senses whether the switch is broken or not. So let's take a look at this code. One of the first things you might notice here is that I've got a bunch of the SPI stuff here talking to the backbox. Now all of these switches are on the playfield, so there's you would think there's no reason for us to talk SPI in this code, and if I wanted to simplify the code as much as possible, that I wouldn't have this SPI stuff in there. But it turns out it's necessary. When I first wrote this code up and tried it, nothing was working, and it took me a minute to figure out why. Now, if you look at the optical switch traces, you'll see we've got this, we're getting power from the backbox connector. I think that maybe that's just out of convenience because the power is actually coming from the battery over here. But what's interesting is, aside from that, we've got a trace, this yellow trace, from the backbox connector using this mysterious BPC6 pin. And that goes to a transistor of some sort that is controlling whether power is even applied to the emitters and receptors of these 3 optical switches. So something from the backbox is controlling this transistor. I don't show it here just out of simplicity, but when you look at the whole picture, not only can we control whether these diodes are grounded, whether they have a path to ground at all using the output pin, but we can also control, or something is controlling, whether power is applied here. So we control the source of the power, and we also control how the power and if the power is synced anywhere to ground. Anyway, long story short, I actually had to enable the slave microcontroller by providing it the startup code, this blob of startup information, before I could get any power at all through these two diodes. So that's why you see the SPI code here. It's because I have to initialize the slave microcontroller to get this pin to be in the right state to pass power through this transistor and enable the rest of the circuitry here. So that's why this SPI code is here. So you'll see the same SPI code that we've seen before, where we have the ability to send words to the micro, and we initialize it we use that code to initialize the slave microcontroller with this binary blob of data. And we've got the same SPI pins that we have been using previously. But what's new here is the pins that are used for the optos. So each of the three optos has a pin that is an input pin that's used to sense high or low, sense whether the beam is broken or not, and the enable pin that is used to provide ground for those photodiodes. So we've got three sets of sense and enable pins, the shooter lane, scoop, and the trough. Right now I'm looking at the trough switches, so we'll take a look at this switch here. And we're still using the bonus light to indicate whether the switch is open or closed. So when we interrupt the IR beam between the emitter and the receptor, then the light should turn off. So in the setup function, we're still setting up those SPI pins. That's the same as it was before for the score digits and the other lights in the playfield. What's new is configuring the sense and enable pins. So the enable pin is configured as output, and we'll almost immediately set that to low to enable the circuit, provide a path to ground. And the sense pin is set to an input. Not an input pull-up, as we talked about with the previous circuit, because the power is actually provided by the playfield. So this is just purely an input pin like it was for the start button. So we configure the sense pin as an input, we configure the enable pin as an output. We'll set that enable pin to low to enable the LEDs, but they're not enabled. They're not actually, they don't have any power applied to them until we send this binary blob of startup data to the slave microcontroller. So we do that. And at that point, we'll have power applied to the circuit. We'll have a path to ground in the micro. And all we have to do is read the state of the sense pin. So if that pin is low, that means the IR beam has been interrupted by the ball. So at that point, we'll turn off the light to indicate that the switch has been interrupted, or the IR has been interrupted. If it's not low, if it's high, then the ball is not interrupting the switch, so we'll turn the light on. So it's low when it's interrupted, and it's high when it's not. So let's give this code a try. So we've got the LED is on, meaning IR is uninterrupted. It's flowing freely between the emitter and the receptor. If we interrupt that IR beam, then it turns off. We can roll a ball through and see how it looks. So you can see a brief moment where the LED is off. All three of these optos work the same. So if you put all of those switches together, you can demonstrate all three of them. The trough switch, controlling the bonus and starlight. The shooter lane switch, controlling that right stand-up light. And the scoop switch, left stand-up light. Got the pops, stand-ups, and the slings. Next, let's talk about the motor on the playfield that provides extra action to the pop bumpers. There's a good amount of circuitry involved with this. The original micro isn't strong enough to drive the motor directly, and neither is the Teensy. So they will both need to use this transistor here, which controls the path to ground for the motor. So the motor is directly powered by the battery coming in from the main connector. It goes straight to the motor connector. The motor is behind these two pins here. So power comes in to one side of the connector, and then it returns looking for a path to ground on the other side of the connector. That path to ground is controlled by this transistor, and the transistor is controlled by the microcontroller. So you can see we've got one trace coming from the micro through a resistor to the base of the transistor. When the micro enables that transistor, then the motor has a path to ground and it begins turning. When the transistor is not enabled, the motor stops because it has no path to ground. So we've got one trace that enables this transistor. We've got one trace that provides power to the motor, and then ground comes to the transistor and then back to the main connector. The other component we've got here is a diode that is connected across both of these pins on the motor connector. We'll take a look at that in a minute when we look at the more detailed circuit schematic. But the motor is controlled by a single pin on the micro, an output pin that provides either high or low, which enables or disables this transistor. So taking a more detailed look, you can see that single output pin on the microcontroller, which is either supplying voltage or is shorted to ground. That goes through a resistor to the transistor. That transistor is providing a potential path to ground for the motor. The power comes from the motor. Power for the motor comes directly from the playfield. Power comes in on one side, and then the motor is grounded through the transistor. The other component is this diode that is going across the motor. So it's connected on one side to power and on the other side to the potential path to ground. It's called a snubber diode, and you have to put those across any kind of inductive loads. You see this on full-size pinball machines. If you've got a coil, like a flipper coil, most of the time you'll see on the coil there's a diode that goes across those contacts. What happens is when you build up power going through that coil, and then you suddenly disconnect the ground path, there's a large reverse voltage surge that if it doesn't have another path to follow, will just go to other components in the backbox or on the playfield and potentially fry them, because it can be, the voltage of that surge can be many times higher than the original source voltage. So having a diode put across that inductive load in the opposite direction dissipates that large voltage surge. So normally this diode isn't even coming into play because power is coming in. It can't pass through the diode in the direction from power to ground. So the power has to go through the motor. It can't go through the diode. It's not until the micro disconnects this ground source that this reverse voltage surge can flow this direction through that diode. And that causes it to, it gives it an alternate path so it doesn't traverse up to this voltage source or to the microcontroller. So that's the purpose of this diode that's reverse biased across the motor. Pretty simple from the microcontroller perspective. It's just a single pin. So let's take a look at the code that makes this happen. We've got one pin that I've got connected on pin 1 of the Teensy. We're configuring it for output, so it'll either be high or low, high providing voltage or low connected to ground. And all we have to do is set that pin high to turn the motor on, or low to turn the motor off. So we'll have it on for 5 seconds, and then off for 5 seconds, and then repeat. So let's take a look at this code in action. On for 5 seconds, and then off. The last component to take a look at is the speaker. The speaker is driven by 2 pins on the micro, a positive PWM signal, pulse width modulation signal, shown here in red, and a negative PWM signal, shown here in gray. The negative signal goes through 1 or 2 resistors. The second resistor is optional. The selection between those 2 resistors determines how loud the speaker is. So there's a switch on the bottom of the cabinet marked high and low. If it's set to the high position, then the audio path goes through only 1 resistor. If it's set to the low position, then it goes through 2 resistors. Let's take a look at that circuit. It's 2 pins on the micro, 1 positive PWM signal going straight to the speaker, and then the negative signal goes through 1 or 2 resistors depending on whether this switch is closed or not. If it's open, as shown here, then it has to go through 2 resistors, making the total resistance higher. If it's closed, it can bypass that second resistor and just go through 1 of them, making the speaker louder. Now, I don't have the speaker hooked up, and I don't have any code to show because it's going to require some extra hardware to drive that speaker. Although the Teensy can produce PWM signals, they're not going to be strong enough to drive a speaker directly. It's going to need some amplification. And also, if I want some high quality sound, I'm going to need some extra hardware to do that. One of the reasons I chose Teensy is because they offer that hardware. So there's an add-on board for the Teensy that can drive speakers. And it's got some provisions for some extra memory in case I want to include some digital sounds or music when I make the new audio package for this new machine. But it requires several more pins, and I've pretty much exhausted all the pins on this small board. I've got a few left over, but not enough to drive this audio board. So I'm going to have to get familiar with the audio board. I'm probably going to have to move to a new version of the microcontroller, a new version of the Teensy that supports more audio pins. So there's a larger board. This is the 4.0 board that I've been using so far. There's a larger 4.1 board that has more breadboard accessible pins, but it's also got a bunch of other stuff on it, like Ethernet and some stuff that maybe I don't need. I could use the Teensy 3.6, which again offers more pins. It doesn't have some of the stuff I don't need, like the Ethernet driver. But regardless, I'm going to have to move to a larger micro and get familiar with this audio driver board. Pretty much, change this whole situation just to drive audio. Now that all the lights and switches and display and motor is working, the next step is to get the speaker working. To do that, I'm going to have to use this audio adapter for the Teensy that gives amplified audio output. And to get that working, I'm going to have to get some more accessible pins, because you can see I've used up nearly all of the I/O pins on my smaller Teensy microcontroller. So I'm going to have to get some more breadboard accessible pins, and to do that I'll have to step up to the 4.1 version of the Teensy. So this is the 4.0 that I've been using. This is the 4.1. It uses the same processor, but it's got a lot more peripherals on the board, and you can see it's got a lot more pins accessible, and that's what I need. So in the next video, I'll tackle moving the code over to the 4.1 version of the Teensy and getting some sounds working on the audio controller board. Thanks for watching. See you next time.